PDP 11. Now, Ken Thompson and Dennis Ritchie were in Bell Labs, and they found the PDP 7 out in the hallway, unused, so they kind of got it. And you'll appreciate this. Of course, there was no operating system on the PDP 7 that they could use, and so they created their first version of Unix, writing it in assembly language and cross-assembling it, put it into paper tape. And they took it over to the PDP 7 and loaded it in. Now, after the PDP 7 kind of ran out of steam, they said to the boss, hey, we'd like to move it to a larger computer, but you know, computers are pretty expensive back in those days. And so they looked around in Bell Labs for somebody that would finance this, their little project. And they couldn't find anybody. Till finally they found one department inside of Bell Labs that would fund this and buy the computer for them. And you can guess what department that was? The department inside of a research facility that has money unlimited. Guess. No. The legal department. And Ken and Dennis convinced them that they were going to write an operating system where the lawyers could sit down and type in their legal briefs and format them and everything else, and it'd be beautiful legal briefs. Now I'm going to take you back to those days. Remember, they're using a dot editor on an ASR 33 teletype, and can you imagine a lawyer using a dot editor and then putting it through TROF? Yeah, I can't either. And that's why they developed legal secretaries there in Bell Labs, people who were smart enough to do that. We had some of those people in Bell Labs, the legal secretaries and documentation administrators back in those days. And people say that Unix was hard to use, but these people were writing their own shell scripts, eventually created their own databases to hold their files. They'd hold little meetings talking about how to program Unix better. And this is one of the reasons why Unix was so character-oriented, was because it was aiming towards satisfying the legal department that their money that they had invested in it was worthwhile. Okay, but we're not here to talk about that today. We're here to drink beer, play games, and I'm going to give you this little talk about this program that I'm working on. And I call it optimization. And first of all, a lot of you who know me know I go around talking about free software, and a lot of times about the commercial business side of free software, the money-making side or the money-saving side or the freedom type of side or stuff like that. You don't really think of me as a technical person, but that's what I started off being. I started off being an electrical engineer, and after being almost electrocuted by 13,600 volts and 800 amps, I decided to go into software because it was a lot safer, you know, in a nice dry room with no humidity and 5 volts at a milliamp do it to me. The worst thing that could happen to me is to get a paper cut. And after I graduated from college, I worked on IBM mainframes for 5 years for Aetna Life and Casualty. And I learned IBM assembly language there. And then I went to work for a small 2-year technical college, and then in 1988 I learned Unix. I became a Unix systems administrator without ever having seen a Unix system before. They hired me like that. And then in 1994 I met Linus Torvalds, and we'll get more into that later. But I've worked for lots of different companies in lots of different areas, but I still do like technical things. In 1994 I met Linus, and I was at a Deacon's. I'd never heard of Linux before, never heard of the project, but a friend of mine convinced me to go to my management and get $5,000 to fly this guy from Helsinki, Finland, down to New Orleans. Now, those of you who know New Orleans, you know it's the adult Disneyland. You can get anything you want in New Orleans and a lot of things you don't want. And so Linus came down there, and sat down, I used Linux for the first time. Now, by this time, I'd used Xenix and Minix and System 5, System 3, System 4, System 5 Berkeley. I used all these different Unix systems. And when I sat down to this, that was on one of those stinking, miserable, crappy Intel PCs, it was like playing a piano. Now, if you tune a piano, you can typically get fairly good music out of it. But if it's a really nice piano, all the keys are perfectly weighted and they're all even. It's just a joy to play. And that's what this was like. It was really, really nice, even though it was on one of those miserable, crappy Intel PCs. Because Digital made real workstations, VAXs, MIPS machines, alpha processors, stuff like that. Not those weak, miserable, crappy Intel PCs. So I saw this, and I heard Linus's talk and everything, and I thought about this as a wonderful thing to do research. Research into very large address spaces and what can be done with very large address spaces, plus changing Linux from a CISC system into a RISC system. So be able to do research in RISC optimizations in the compilers and stuff like that. And so I took him out on a riverboat, and you'll see more about that later. And I convinced him to do the port, and I got him an alpha processor to do it with. And then in 1995, I became the executive director of Linux International, where we did things like defend the Linux trademark from being taken over and created the Linux Professional Institute for certification of systems administrators and started the Linux Standard Base project, which I still feel very passionate about. And then after that, I went around promoting Linux worldwide. Now, over the last couple years, I've actually had people tell me CPUs, the desktop CPUs are fast enough. Now, I've been hearing that for 43 years. Of course, back when I first heard it, you needed a desktop made out of concrete or stuff to hold the computer. But everybody, computers are fast enough. Computers are fast enough, and we know that's not true. And I've also heard from a lot of university professors that Java is the only language you need. I said that to somebody today. They said, no, you need small talk. Okay. And nobody codes in assembler language anymore. Now, I coded in assembler language for 7 years. And granted, some of the things I did probably I could have done in a higher level language. But the assembler language is useful to me, and I'll show you why in a moment. And finally, virtual machines make architecture knowledge obsolete. You don't need to know anything about the underlying architecture because the virtual machine is going to hide it from you or protect you from it or something along those lines. And finally, the last comment on there, standards are as interesting as a Russian truck. That came from Ken Olsen, the CEO of Digital. And the reason I threw that in there is because Ken was an engineer. And what he hated about standards was the nitpicking, arguing, twisting hours discussion about what the standard was going to look like. But once the standard was defined, as an engineer, he felt it was his job to make it run faster, in a smaller space, more economically, more scalable. That was what he was all about. And I think that that's what performance is all about, is to the standards, making things work faster, better, more stable, more scalable. So when I talk about performance, and this goes back to our CPUs fast enough, I talk about, when I talk to students, I say, I do real problems. Petabytes of data. We talked about, you saw a talk today, xenobytes of data, I think that was what it was. Really huge amounts of data, thousands of processors working together with tens of thousands of threads all working on the same problem. On the opposite side of the coin, real time. And the definition of real time to me is fast enough, and consistent enough. In the early days of Linux, I said to Linus, you've got to make the kernel better soft real-time. He says, no, 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 it's good enough. I said, how can you say that? He says, when I play Quake and the monster has a gun in its hand, I point the gun, he points a gun at me, I hit the button, and I kill the monster. Real time. I said, Linus, put a real gun in the monster's hand. He stopped and thought for a moment and says, okay, you're right. And the next time the kernel came out, the soft real time was considerably improved. I don't often argue or talk with Linus about kernel things because I figure there's enough people doing that, but every once in a while I'll catch him on something. Cell phone apps. The faster the application gets done, the more likely the cell phone is able to go back into a state where it can save power in the battery. So you get battery life. If your program is taking too long to execute, it's going to stay active, your battery is going to drain. So all of these things are things that can actually help. And the same thing is true in servers these days. If the server becomes idle, it powers down things. And what that means is we can save a lot of electricity in places like this. This is Itaipu, which is the world's largest hydroelectric plant. It's in Brazil. It's the largest capacity, I should say. Three Rivers is actually a larger plant, but the rivers that feed it don't have the power of this river. And if we can cut back on the amount of electricity that computers can use, that means we can have fewer fossil plants going. If we cut back on electricity overall. And the great thing about electricity is it's analog. So as soon as you cut it back, it balances itself through all of the circuitry. And you can actually, as you cut back, you can actually allow yourself to turn off power plants and stuff like that. So it's good. Now, my first language was Fortran, spelled all capital letters. And there was no Fortran 2 or Fortran 4, it was just Fortran. But my second language was PDP-8 assembler. And I loved that language because every single instruction was exactly the same size. It was very easy to place those assembly language instructions in memory. All of the data tended to be the same size. And it was such a simple instruction set. It only had 8 basic instructions, 0 through 7. And one of those was kind of instruction that did shifting and all that type of stuff. But very, very simple. The machine could not subtract. You took the 2's complement of the subtrahend and you added it to the minuend, and that was subtraction. Does this sound familiar? As opposed to the PDP-11 instruction set or the Intel instruction set, that you look at those, you can't tell how long the instruction is or how long it's going to take to execute. It was a great instruction set. And I learned it from a book and plenty of practice. Nobody told me that assembly language was difficult to do, so I just did it. So I think that's another thing. We always say, Unix is hard, and so we convince other people it is. But maybe it isn't. Maybe it's actually no harder, really, than Windows. Assembly language really helped me in my past because there were times where I found compiler errors. I know you guys never see these, okay? But believe me, there were times where COBOL programmers would come to me or other high-level language people come to me and they say, I've been staring at this code for hours and I don't see my mistake. I look at it and I say, you haven't made any mistake. You coded it correctly. And they said, well, what's wrong? I said, the compiler made a mistake. And the compiler made a mistake? I says, yeah, it was written, the compiler's a program just like you guys write programs, right? And it makes a mistake. The guy had a bad day or, or drank too much beer or something. No, I can't, not too much beer, there's no such thing. Had a lot of beer, okay? And it made a mistake. And so sure enough, we generate the assembly language, we look at it, and I can point, say, right there. You coded this, and it's doing that. Mistake. Another time, there was a program that was taking exceedingly long on an IBM mainframe. When you ran the program, not only did it run slowly, but every other program on the system started to slow down. And every other program hooked to any computer that was even near that one slowed down. And I took a look, I profiled the program. I found out that one machine language instruction was taking up 99% of the wall clock time. One machine language instruction. IBM instruction set, can anybody guess what it was? Read the clock. Now that sounds like an innocent enough instruction, right? Read the clock. However, that particular instruction was used for synchronization of CPUs in the system. And so in order to read the clock, you had to stop all the I/O. You had to flush all the buffers. You had to flush all the cache. You had to stop, and not only for your CPU, but every CPU that was even anywhere remotely connected. And then you read the clock. And then everything started back up again. And I asked the guy, why are you reading the clock? He says, I want to find out what day it is. I said, couldn't you do that one time at the beginning of your program instead of the 300,000 times you're doing it as you read each record off the tape? Oh yeah, I could. I could store that in a variable, couldn't I? Yeah. And the next time he ran his program, it went so fast the operator thought it had ab-ended. Or EBCDIC. How many people know what EBCDIC is? Yeah, EBCDIC is ASCII gone bad. EBCDIC is the coding used in IBM systems, and it doesn't follow any logic whatsoever. But there's 4 instructions in the IBM instruction set. Convert EBCDIC to pacdecimal and pacdecimal to binary. And that was 2. And there's another one, convert binary to pacdecimal and pacdecimal to EBCDIC. And if you make a mistake and hold the index to your array in COBOL as a picture 9 field, you will do that conversion every single time. And those are the 4 longest instructions other than read clock in the IBM instruction set. So these are the reasons to know assembly language. David Mossberger Tang, who helped us with the alpha port for Linux, did an array, multiplied an array, and because the second array was so big, every time you fetched an element from that array, you caused a cache miss. So what he did was he inverted the second array, did the multiplication, inverted the answer, which gives you the same result, and it went 40 times faster with an alpha. It only went 10 times faster in an Intel system because the Intel system didn't have as much cache as the alpha did. And so this was something which really helped out with the cache. And then how many of you have ever done programming with tapes? Yeah. I love tapes. Yeah, there's basically 2 types of tapes and they both suck. So there's one which is start-stop tape. Those are the old real tapes you see, and there's a 3/4 of an inch inter-record gap in between your blocks. And then there's the streaming tapes that you have to try and keep them streaming, and if you can't, they write out nulls to take up most of the tape, so you can't tell how much capacity you're going to have on any tape. And both of these, if you don't understand the architecture of the tape, your program's going to run very slow. In the early days of the X server, we had a bunch of engineers who were coding on the X server with GCC. And we decided that the VAC-C compiler, which normally produced code that ran about 30% faster than the code that GCC generated, was a good thing for the X server. So what we did was we took the VAC-C compiler and compiled the X server and tried to see how much faster the X server would work. And the answer was 0. 0 performance improvement. Why? Because the engineers knew so well how the GCC compiler was going to generate code that they would twist their source code in order to get the best optimization. In fact, what they were doing was they were doing the optimization for the compiler. And the VAC-C compiler got no additional optimization out of it. So these are things around performance that are kind of tricky, and if you don't know about assembly language, and if you don't understand about the architecture of the computer, then you're in trouble. So again, when I met Linus, I took him out on that. That's a Natchez. That's the last steamboat that goes up and down the Mississippi River. All the other boats are actually diesel boats. And what I didn't know was that Linus loves steam engines. He likes steam engines, he likes Stirling hot air engines, he likes mechanical clocks, all that type of stuff. And I took him out on this boat, showed him the steam engine, and convinced him that he really wanted to do the Alpha port. Because what I wanted to do was to have Alpha Linux to allow universities to do research in new algorithms. How many of you have ever read The Art of Programming by Donald Knuth? Yeah. Volume 3, Sorting and Searching Techniques. You are aware he's rewritten that about 3 times. Yep. 16-bit to 32-bit, 32-bit to 64-bit, you know. I have a friend of mine who wants him to do it for 128-bit virtual address space, but I said, you know, well, in what universe are you going to have the page table for that? But he hasn't quite changed the algorithms. I'd love to see him change the algorithms for the 64-bit port. But the Alpha project was much the same as what you're about to go through, taking 32-bit code and making it 64-bit. We had a group at the Digital Semiconductor Group, headed up by Andy Reeves and Jim Paradise, and Dave was part of that group, who, independent of what I had done with Linus, had decided that Linux was a good match for the Alpha. And they were doing a 32-bit port of Linux. And I said, why? Because one of the big selling points will be this address space. And they said, well, it's going to be hard because we have to port all the applications to be 64-bit. And I said, no, the applications have already been ported. The GNU software already worked on DEC Unix. You know, that part is done. The part that we need to do is exactly what this project is going to be doing. Getting the 32-bit assembly language inside of the Linux code to be 64-bit and ready. But with the Linux port, even though there was a lot more work to do, it only took 9 months for the community to do it, which was truly amazing. Now, one of the reasons why I wanted to cover this was an interesting thing that happened during this port. Digital had this math library that we had spent a huge amount of money making one of the fastest math libraries in the world for the Alpha. And Digital was willing to contribute the binary copy of the math library to the Alpha Linux project, but they weren't willing to release the source code. And of course, the open source community was really upset about this. They wanted to see the source code for the math library. And I kept being beaten up about that by the open source community. I kept getting these emails asking me to try and convince my management, and I knew that was impossible. So one day, I sent an email to them. I said, if you guys are such hotshot programmers, you write one that's better. And there was silence on the other end of the Ethernet. And then a couple days later, I got this email message that said, sine is 2% faster. A couple days later, cosine is 1.5% faster. And line by line, subroutine by subroutine, down through the math library, every single subroutine was now faster in Alpha Linux than it was DEC OSF1 Alpha. Except for one routine that never was any faster. And I found out why. Nobody used it. Nobody cared. So it stayed the same speed. Now, I can't remember. I can't remember which one, but it was one of those odd mathematical routines that, you know, somebody had done it at one time, but it just didn't, not that many people used it. Today, we have college students learning Microsoft Office and Oracle instead of Office systems and databases. I mean, I tell people, I don't care if people want to teach Microsoft Office in a university as an example of an Office system. I don't care if they want to teach Oracle as an example of a relational database. But they should be teaching other databases too, and they should be teaching data structures, and they should be teaching how they work so that people can make a decision about which is the right one to use. And a lot of them are using virtual machines instead of real iron. And I think that a lot of kids really love to use real iron. And so what happened with the University of Cambridge is they recognized that they were getting students today that know less about computers than they did 20 years ago. Because 20 years ago, you got a Kim 1, or you got an Altair 8080, or you got something that maybe you had to cut out a soldering iron and solder some resistors and capacitors and stuff like that to. And you typed in a program that came off out of a magazine. And usually when you typed in the program and then you said run, and the thing would say syntax error. And then a month later, the magazine would come and say, oh, we had this problem, you know. But by that time, you'd figured it out. But today, kids go and they get a computer from the store, they never open it up, they get games, they put on there, and maybe they write a little HTML and they think they're programmers. That's a problem. So this is why the Raspberry Pi people created the Raspberry Pi, is so that they can get these things out into the hands of high school students, not college students, but high school students, so that by the time they come into the university, they'll actually understand something more about computers. And this is reflected by a friend of mine who recently was trying to hire a programmer, and the programmer came in and said, oh yeah, I've heard about cache. It makes the computer go faster, I think. And the guy, yeah, this is bad. So a short time ago, I was at the University of Cambridge, and I ran in, and yes, John, did you want to say something?
Yeah, I'm just going to add, I sent a graduating class of computer scientists a questionnaire a few years ago. One of the questions was, what's a stack? You would not want to see the answers I got.
We'll talk afterwards. So a few months ago, I was lucky enough to run into Dave again at the University of Cambridge, and I was giving a talk there about Project Kawa, and Dave had come to give a little bit of talk about Linero and ARM and things like that. And we started talking, and you know, we've done some work in the past and stuff, and Dave said, we got this problem where we have this 32-bit code that is going to have to be changed to go to this 64-bit processor. And that we have done some investigation. Steve McIntyre had done some investigation and found out there were about 1,400 different modules inside of the Linux system that have this assembly language in it. And they looked like some of the assembly language was actually kind of hacked in. In other words, the person had looked at the Intel assembly language and then duplicated that with the ARM assembly language instead of actually thinking about what the ARM assembly language could really do and really engineering the answer. And also that there were places where the same type of thing was done over and over again. And if there had been some type of an intrinsic in the compiler that everybody could use, then when the compiler was changed to generate the object code, it would be fixed for everybody. And then finally, there were some things that maybe, if we really looked at this stuff, we find out that some of this code is a little older. It's come from smaller address spaces and things like that. And what we should be doing is thinking about this in ways of performance improvement instead of just porting. That people would be much more responsive to that. And so we're thinking about looking at this code and the fact that memories are now bigger, less expensive. Not in every case. Of course, we have embedded systems, so we have to be sensitive to that. We also have to be sensitive that we can't change things to make other architectures slower. Everybody has to see an improvement here. And in some cases, the question is today, should it even still be an assembler language? Let's try and see if we can get rid of the assembly so that for all time we can just change the compiler, recompile it, test it, and go on. Or maybe we can use some of those better algorithms. Maybe we can see a real improvement. So in my early days of programming, I took a piece of code that ran in 10.5 hours on a PDP 1170, changed the algorithm, got everything up into cache, and the program then took 3 minutes. And that's the type of thing that if we could find a piece of code to change it to do something like that, that would be spectacular. So this is kind of a pre-announcement of this contest. We want to make it a contest to try and change this code, make sure it runs on the 64-bit port, but also to improve the performance. So measure the performance ahead of time, do the change, measure it afterwards, and write up a little statement that says what you did. Why did you pick that algorithm? How did you make it run faster? Stuff like that. And submit this, and we could have categories of prizes. The percentage of speed up you have. How did you reduce the footprint? Did you make it better, a smaller application? How did you utilize cache and stuff like that, so that we could have different categories of prizes. And with 2 requirements. Number 1, it does have to work on ARM64, and 2, it has to be accepted by the upstream programmer. So here are some suggested prizes. We talked a little bit about this with Dave and Steve Taylor. And ARM development systems as possibilities. Lots of people would love to have those. Come to a Connect meeting and talk about what you did, or perhaps even as a free admission, or perhaps even paid to go there. And of course, the next one's in San Jose, and the one after that's in Korea. And I think that going to Korea for somebody would be a pretty nice prize to win for what might be a lot of fun and a small amount of code. From some side effects from this, I think we might have a lot more people actually learn assembly language and learn about the hardware. And we might be able to get some people, some additional people for different companies as programmers out of this. The people who do this work and do it well, we'll see those people, and maybe some of your companies would like to hire them. And in any case,
can we do internships as well here? I mean, those companies that are here who want to offer prizes, we could also offer internships for people as well.
That's a good idea. And the question was, could we offer internships? Absolutely. And if any other company wants to throw in any type of prize for this, we'd be happy to have your name alongside the prize. You could sponsor various prizes and things like that.
One other comment from an HP perspective, if folks want to sign up as a developer with HP, we'll let you work on real hardware and do the testing and development there in our labs, do remote work.
Okay, the gentleman from Hewlett-Packard says that if you sign up with Hewlett-Packard, you can work on real hardware stuff. Let's brainstorm about this a little bit later, okay? Just a couple more slides here. So we're also going to be looking for mentors. Now, I want to get a university in on this, because I want to get a university to understand that this is going to end up probably being a course in performance and performance analysis. And that a university like the University of Cambridge, or maybe the University of Sao Paulo, could actually publish a lot of this stuff and create a course for it. So the time frame for this is to get your ideas and stuff, and that's why I'm here, that's why I'm talking to you about this, is to get your ideas about this, and to formalize the program at the end of this week. We'll put it up on Google Drive so that people can look at it and stuff like that and comment on it. And then I want to search for a university home for this. and two places that have been suggested so far, University of Cambridge and University of Sao Paulo. And then to publish the rules, prizes, and everything to get people interested, and then have the final judging by the end of the year 2014. And that doesn't mean that the modules are all going to wait to that time. As they're done, they'll be put into place and you know, put up. But we want to give some people some time for some of the harder and not so low-hanging fruit on this. And I don't have all the details today. The details will be coming. I did write an article for Linux Pro magazine, which is going to be published in about a month and a half, talking about this. I have a blog where I'm going to be blogging about this. I'm going to be blogging about different types of performance things as we go along. And of course, I'll be writing some stuff for the Linero website about the same thing. I would like to have a really nice list of resources, books, articles, white papers, stuff like that on optimization. We can put this stuff on the Linero website so that people keep going there and looking at that and learning more and more about optimization. I've got a couple books and things. I'd be interested if you guys have some really good books, you know, or really good articles, just send them to me. Here's my email address. Send them to me, and as time goes on, we're going to create some forums so that people can talk about this and exchange ideas. But I go to places like Campus Party. We have Campus Party in London in September 2nd to 7th. There's going to be 10,000 young geeks there who are very, very interested in computers, ages 18 to 32. Some of them are not so young. Some of them are graybeards. But that's the normal age group. And I go to a lot of other free software conferences where I'll be talking about this throughout the year. So we'll keep up people's interest in this. But I think this is very exciting because I think that we have a chance to maybe boost the computer science, teaching in universities. And we have a chance to say to people, some of these professors, Java is not enough. People need to know how the computer works, even if you're using a virtualized machine. So that's the end of my presentation. And like I said, I'm going to be sitting here for a little while, and you can come up, you can say, if you have ideas, you send them to me in email, and I'll bring them all together and post them in the drive, and then I'll send a note out after a while and say, here's the plans, give me some final comments before we launch this. And of course, the thing is dynamic, so we can change as we go along. Thank you very much. Enjoy the rest of the evening with your games and stuff, and I'll be around.